So this slide is on post-optimality analysis, specifically focusing on factors that affect feasibility. So recall that sensitivity analysis is performed during model formulation. So you analyze so once you formulate the model and you conclude the optimum strategy after performing the simplex method, then you perform sensitivity analysis to determine the ranges of the different parameters that would keep the optimum basic solution optimal. We use the changes in the so there were two. You have the changes in the objective function coefficients, which is used to identify how much it can increase or decrease while keeping the same optimal solution. We also had the concept of shadow prices, which are used to quantify the impact of changes in the right hand side of the constraints. Okay, so in performing sensitivity analysis, we did not need for recalculation of the simplex method. However, in reality, there are changes in the parameters of the model, usually or after optimality, such as additional constraint or additional decision variables. These are cases that would require periodic recalculation. And this is the process or the step called post-optimality analysis. Now, this reflects how reality is. So, for example, if you are an operations manager or an operations analyst, given the conditions or the parameters that a company is providing you, you construct a model that will optimize their operation or the process. And then after that, you present it to them. Okay, so this is the optimal strategy. However, at that time, there could be changes due to fluctuating market prices or demands or some other factors that could affect. So sometimes, or it could just be an idea from the company or from the business. So that would be the time when you would do post-optimality analysis. So that would require periodic recalculation, which highlight the need for ongoing evaluation of the model as real-world conditions evolve. Okay, so it is applicable in contexts such as in business and other operational contexts wherein conditions change frequently due to several factors such as fluctuating costs, resource availability, or market demand. So there would be a need for regular assessment or reassessment of the optimal solution to know if it is still necessary or to ensure that the strategy that you are using still remains effective. So in such cases, the primal dual relationships of the LP are useful in performing post-optimality analysis. So here are the following cases wherein this is applicable. So for example, if the current solution remains optimal and feasible after some changes, then there would be no need or no further action necessary. But if the resulting solution after the changes are implemented becomes infeasible, then there is a need to use dual simplex method to recover feasibility. If the solution becomes non-optimal, then you will have to perform another primal simplex method with the changes implemented to recover optimality. If both optimality and feasibility are having issues, then you would need the generalized simplex method to recover both the optimality and feasibility of your LP. Okay, so let's discuss the different simplex methods. So first is the primal simplex. This was the original simplex method, or this is what we call the standard simplex method. It was developed by George Dantig. So it starts with a basic feasible solution, and then it moves towards optimality. So each iteration improves the objective function value while keeping the solution feasible. So you can liken it to a mountain climber who starts on a trail, and then if you do mountain climbing, there is, and then for you to reach to the peak, there is a declared trail that you can walk on, or we call it a safe walkable path. So the climber would start at the beginning of the trail, and then he moves towards the peak while keeping his path, or while keeping his footsteps within the safe walkable path, and until he reaches optimality, or the desired peak. So in dual simplex, it starts from a solution that is already optimal but not feasible. So you can liken it to a climber that is already at the peak, but he could be standing on an unstable ledge, meaning his footing is not secure. So in LP, this is a case where feasibility is violated. So he would need to move to a stable ground or safe zone without changing altitude. So that you'll be able to still move to a safer path or a safer ground, but you are preserving optimality. So in this case, every iteration would gradually restore feasibility until an optimal point or value is achieved inside a feasible region. The general simplex case or simplex method is a case that considers both issues, optimality and feasibility. So this would be the case where you start with a non-feasible and non-optimal, or what you call a suboptimal point. So what the climber do is he moves to us. Every iteration would help him move to a safer ground as he moves towards optimality. So it could be that he starts here, and then he moves. Every iteration would move him to a safer ground and then towards the peak. Okay? So what does this mean? Each iteration improves the objective function value, with the solution slowly going back into the feasible region until feasibility is restored. So every iteration should be an improvement. Okay, so let's go back. So in performing post-optimality analysis, we consider two possible scenarios. Changes in the right-hand side of constraints and addition of new constraints. Now, changes in the right-hand side of the constraints can be caused by changes in the daily capacity of operations, or a shift in the stack capacity of one operation to another, while addition of a new constraint means an additional operation. Okay. So changes in the right-hand side constraint could mean an increase or decrease of the value. When you have an increase, it means you are increasing the right-hand side of the constraint, and it allows a broader range of feasibility solutions, while decreasing the right-hand side of the constraint tightens the constraint. So there are two things. Increase is to relax or to broaden the range of feasible solutions, and decrease means to tighten or to constrict the space. So when there is a decrease in the right hand of the constraints, a consequence of that would be a reason for that is a consequence of that is that it could render previously feasible solutions to be non-optimal, or it might also lead to no solutions if the constraint becomes too restrictive. So in this case, it would require a recomputation of the right hand side of the tableau using this formula. Okay, so let us consider the Toyko problem. This was a problem about a manufacturing company named Toyko that produces three types of toys. So the company wanted to maximize its revenue while satisfying limitations with respect to availability of time in three operations. So let's say operation 1 is manufacturing of toys, operation 2 is painting, and operation 3 is polishing. The decision variables x1, x2, and x3 represent the number of toy trains, toy trucks, and toy cars respectively. If you also recall, the optimal solution says that it is best to produce 100 toy trucks, 230 toy cars, but none of the toy trains, and it yields the maximum revenue of $1,350. So, and then this was also the dual of the problem. Now this is the optimal tableau that is based on the primal of the LP of Toyko. So x4, x5, and x6 are the slack variables. So note that the current basic variables are x2, x3, and x6. Note also, or recall also, that feasibility of the current optimal solution is affected only by changes in the constraints. That is, it could be due to changes in the right-hand side of the constraints or due to an addition of a new constraint. And infeasibility occurs when either of these changes cause the current basic variables to become negative. So it would be a negative value here. Again, we know that x4, x5, and x6 represent the slack variables. And if you recall, in the initial tableau, these slack variables were the original basis or the initial basis of our solution. So these columns here were the columns, initially the columns of the identity matrix. So this was our basis. So this composed our basis. So in every iteration, what you see here in this area where is the inverse of the initial basis. So now to verify the solution, a change in the right hand side would require recomputation based on the product of the inverse of the basis in the iteration and the right hand side of the constraint. So if you look at it, if we multiply this with this gives us the value of our current basis. Okay, so now suppose that the daily capacity of operations 1, 2, and 3 are increased to 600, 640, and 590 minutes. So we will use the same formula to compute the basic solution. This results to a new values for the optimal basic variables. So how do we do that? Here. These were the proposed new right-hand side values. We multiply it to the inverse of the basis, and this gives us these new values: 140 for x2, 320 for x3, and 30 for f3. And if you substitute this to the objective function value, this gives you a revenue of 1,880. Now notice that in the original optimal solution, there is a slack of 20 minutes for operation 3. If this slack capacity is shifted from operation 3 to the capacity of operation 1, then we add 20 to operation 1 and then subtract 20 from operation 3. So multiplying it to the inverse of the basis, we get the resulting values for x2, which is 110, and for x3 is 230, nothing changes, and for s3 is negative 40. Now, a slack of negative 40 results to an infeasible solution since we need more time to perform operation 3 than what is allowed. So in this case, we need to recalculate, but this time we will apply the dual simplex method to recover feasibility or to bring the values of the basic variables into the feasible solution space. Okay. So let's recall optimality and feasibility conditions. These are designed to preserve the optimality of the basic feasible solutions as the solution move towards, or at the iteration move towards, feasibility. Now, the dual simplex method is useful in recovering feasibility when the optimal solution becomes infeasible. So similar to what just happened in our illustration or our example. Okay, so again, it starts with an infeasible solution, but it is optimal or better than optimal. So basically, it is suboptimal. So this method makes use of the dual feasibility condition and the dual optimality condition. Now, the dual feasibility condition is used to identify the leaving variable, while the dual optimality condition identifies the entering variable. Okay. So, under the dual feasibility condition, we choose a leaving variable, which is the basic variable with the most negative value. Okay, so this variable leads to feasibility, meaning we allow more changes or more improvement. And then the algorithm ends when the variables are all non-negative. So after choosing the leaving variable, the entering variable is then chosen to be the one with the negative non-basic variable alpha sub rj, and this corresponds to the minimum ratio between the jth reduced cost and the alpha sub rj. So the minimum value for this would give us our entering variable. Now, if this alpha sub rj is greater than 0 for all non-basic variables, then the problem has no feasible solution. Okay. So in summary, dual optimality condition requires the following things. The objective function must satisfy the optimality condition of the regular simplex method. So this means that for a maximization problem, the entering variable is chosen to be the non-basic variable with the most negative coefficient in the Z row. It follows through the regular simplex iteration, and the optimum solution is reached at an iteration where all Z row coefficients are non-negative. So additionally, all constraints must be less than or equal to the inequalities. So in this case, when the inequality is a greater than inequality, we convert it to less than by multiplying both sides by -1. Okay, so let's skip this part now. How about if instead of changing the right-hand side of the constraints, we decide to add a new constraint or an additional operation? Okay, so what happens? So when we add an additional constraint, we consider two cases. The case one is when the new constraint is considered redundant, meaning it has no effect on the current solution. If it is not redundant, then the current solution does not satisfy this new constraint, so we need to recalculate using the dual simplex method to solve for a new solution. Okay, so let us consider again the Toyko model. So we have the primal and the dual of the model. And then now suppose that there is a need for a fourth assembly operation with capacity 500 minutes. So additionally, the time per unit of the product for these new operations are 3, 1, and 1 minute respectively. So this creates, or this gives us an additional constraint given by this inequality: 3x sub 1 plus x sub 2 plus x sub 3 less than or equal to 500. If we substitute the optimal solution and check if it satisfies, we get 330, which is less than the capacity of 500. So this means that this new additional constraint has no effect on the optimal solution. So therefore, this new operation is considered redundant. Or again, it does not affect the value of the current optimal solution. So the case earlier, you just let it be. But what if if we change the additional assembly operation, we keep it at 500, but we change the times per unit. So for operation 1, we have 3. For operation 2, we also have 3 minutes. And for operation 3, we have 1 minute. So this gives us this new constraint. And if we substitute this, the optimal values to the constraint, we get 530, which is greater than 500. So it's beyond the capacity. So what do we do? This means that, or we interpret this as the current optimum solution not satisfying the constraints set on the new operation. So therefore, we need to implement the primal dual simplex to fix this issue. So first thing to do is to update the model. So now we consider the additional constraint. So this is the model in canonical form, and then we update the tableau. So if you notice, this was the original optimal tableau. Now we add the new constraint. So we let x7 be the variable, the variable that represents the slack for this new constraint. Okay, so these are the values, the resulting values of our variables. And then, okay, so the adding x of 7 in the basis ruined the columns of the other basis variables. So recall earlier that when a variable is in the basis, its corresponding columns should be the columns of the identity matrix. So you have x sub 2, x sub 3, and x sub 6. Now adding x sub 7 to it augments another row on each vector, making them not a vector or not a column of the identity matrix. So we have to do something about it. So we will use this formula to update the row corresponding to x sub 7. Okay, so meaning we will aim to zero out 3 under x sub 2 and 1 under x sub 3. So we use this formula. So it's just Gaussian or Gauss-Jordan. Okay, so what happens now is we have this new row for x sub 7, and if you notice, it is negative 30. So meaning we have to let x sub 7 leave the basis. Okay, so this x sub 7 will be the leaving variable. Now we identify our entering variable. So before that, we solve for the ratio. So this is z over the corresponding values here. So if you look at it, the minimum is 2/3, which corresponds to x sub 4. So meaning we let x sub 4 enter. Now the current basic variables would be x sub 2, x sub 3, and x sub 6. So they remain feasible. And then we have an additional x sub 4. So what does it tell you? So this means that the addition of a non-redundant constraint for operation 4 is not recommended since it lowers. If you notice, the original optimal solution was 1,350. Now when we added the new constraint, we had a resulting new objective function value, which is 1,330, which is lower than the original. So it was not redundant, but it's not recommended because of the decrease in the objective function value.